All right. Good morning or good afternoon, everybody. So welcome to the coaching seminar today. It's my great pleasure to introduce Richard Gustavson from Manhattan College, and he'll speak about developing an algebraic theory of integral equations.
Thank you. Thank you for the invitation to speak. Thank you, everybody, for being here. This is joint work that I've been working on with Li Guo and Yunan Li for the past couple of years. Let's see. All right, so let me just start by saying what is an integral equation? So an integral equation is any equation in which an unknown function appears inside of an integral. So here are some examples. You notice that you are allowed to have iterated integrals. You're allowed to have products of integrals. In this case, f and g are the unknown functions. You see in these examples, you'll see the upper limit of integration is a variable. The lower limit is a constant. And you'll notice that we're multiplying our unknown functions inside the integrals by these functions like e to the st or sine of x, things like that, which you'll notice are not only functions of the variable of integration, but also function of the limit variable. And that'll play an important role. There are two main types of integral equations. The first one is called Volterra equations. These are when at least one of the limits of integration is a variable, like in these examples. The other type is called a Fredholm equation, in which both limits of integration are constant. For this talk, I'm going to be focusing mainly on Volterra equations, although some of the stuff that we end up discussing does apply to an arbitrary equation, including Fredholm equations. The integrals in Volterra equations in general are the following form. So we're going to fix a lower limit of integration a, our upper limit is a variable x, and we're multiplying inside the integrand our unknown f by some function k of xt, which we call the kernel. And it is important to note, I'll reiterate, that the kernel can be a function not only of t, the variable of integration, but also x, the limit variable. And that's going to play a part when we start trying to perform algebraic operations on these integrals. Let's talk about just a couple of ways that you can solve an integral equation. And this is not an exhaustive list. This is just a couple of examples. So one way is to basically differentiate the equation enough times to get rid of the integral. So here's an example, right? We have this equation, this integral equation. If you differentiate 3 times, eventually the integral goes away, right? And we end up with the following initial value problem. And here we're using the generalized Leibniz integral rule, which you can see above. And you notice that in this, when we differentiate here, if our integrand is a function of x and t, then we end up with another integral once we differentiate. And so it's possible, if your kernel is in a nice enough form, that eventually the derivative with respect to x will be 0, and you just end up with this. So this is one way to solve integral equations, because we know a lot about solving differential equations. This doesn't always work. So for example, it's possible that the kernel is, no matter how many times you differentiate it, it won't go away. So I think in order for this to work, the kernel has to be definite. Also, it's possible when you're dealing with more general types of integral equations, like you have products of integrals, that when you try to differentiate, you're just never going to get rid of the integral. Okay, so this doesn't always work.
A question.
Yes.
So is there any work on directly solving integral equations without going to differential equations?
Yeah, so I'm going to show you another method for solving equations right now. Mm-hmm. So here's another way to solve integral equations. This method we can think of as like a series solution. It's called Adomian decomposition. It works mainly for equations of the following form. And if we assume that our solution can be written as a series of this form, we get a recurrence relation where each yn is given as an integral of yn minus 1. And so we can actually solve for all of the terms in the series. Just to give you an example of this, here is our integral equation, and we set up solving for the yns. We eventually get the following series, which is just sine x. And you can check if you plug y equals sine into this equation that it actually works out. So this is one method. There are other methods. There are a lot of ways of numerically solving integral equations. So not getting a closed form solution, but at least getting a numerical approximation for specific x values. But I just wanted to give this as a background so you could see what some integral equations look like. The focus of this talk is not on solving integral equations, but on trying to construct an algebraic theory for these equations. And the motivation behind this is the algebra of differential polynomials. So just to review what this algebra is.
A question. 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 What questions will the algebraic theory answer?
So that's a good question. We're hoping that we're going to be able to produce some analogs from the differential case, like for example, trying to. So one thing that we've been able to do is when we have an integral equation that involves products of integrals, to convert it into one that only involves iterated integrals. And I'll talk about that later on. So that's one example. We're hoping that we could, say, try to figure out what the solution set of an integral equation, of a system of integral equations looks like compared to the algebraic properties of the equation itself, sort of like an analog of the Nullstellensatz, things of that nature, right? So we have some ideas. We had to develop the theory before we could really start to really dig into the individual questions we have. Okay, so what we're trying to do is we're trying to model this off of what's already been done for, say, the algebra of differential polynomials. So just reviewing how this works, if R is a differential ring and we have m commuting derivations, partial 1 up to partial m, and these all are linear and they all satisfy the product rule, then we can, given a set of indeterminants, y1 up to yn, we can define a polynomial ring over R in the variables y and all of their derivatives, as we see here. And we can turn that into a differential ring by just formally defining the partial j derivation on this element as such. And because we know, because there's a standard procedure for considering differential rings and looking at these polynomials, we can, instead of looking at a differential equation, we can look at the differential polynomial, and looking at the algebraic properties of that polynomial, we can get results about the original equation. And so we'd like to do something similar for integral equations. So let's just see what we need in order to do that. First, we need an analog of a differential ring, right? We need like the coefficients of whatever this integral polynomial algebra will be. So let's see if we can develop that. Let's fix an open interval I and an element A in that interval. That's going to be the fixed lower limit of integration. C of I is the algebra of continuous functions on I. And if we fix a kernel, let's assume for now that this kernel is continuous in both x and t, then we can define the Volterra integral operator that sends a continuous function f to this Volterra integral here, where we have a and x are our limits of integration, and we're multiplying by the kernel. So maybe this should be the coefficient ring. Let's just look at an example of how we would translate an integral equation to an element of this in this form. So the Thomas Fermi equation is a standard equation in physics. It describes the potential of an atom in terms of its radius. It's given here. We have an iterated integral, and we see that we need two integral operators. This outer integral, we're just integrating from 0 to x of f of t, of whatever our integrand is. And then we have our inner integral has a non-trivial kernel t to the minus 1/2, as we see right here. And then the equation becomes this. So it's P1 of P2 of y to the 3/2. And so you see that if we want to be able to study integral equations in the way that they're used in literature, which often have multiple kernels involved, we would need to have multiple operators, one for each kernel. And so the question is, how do the properties of this algebra with this operator, how do they depend on the kernel? So let's look at a couple of examples. The first example is what we call phantom kernels. This is when the kernel is a function just of t alone. T is the limit of the variable of integration. Okay, so in this case, we just get the following operator. And a specific case of this is when the kernel is trivial, it's just 1, and then we get the standard integral operator. It turns out that for any two continuous functions, k and h, for any two phantom kernels, then the phantom operators, pk and ph, satisfy this identity 1 here. And this identity, we call them a matching Rota-Baxter identity. And the algebra of continuous functions together with all of these phantom kernels, then we call it matching Rota-Baxter algebra. This is an extension of the standard Rota-Baxter algebra. If k and h were the same, then we would get the following identity down here. And this is basically just a generalization of integration by parts. So you can see if we let capital F be defined as the integral of little f and capital G is the integral of little g, then the integration by parts identity, which we all know, is right here. And notice capital F is P of little f and capital G is P of little g. So if we just rearrange the terms, we end up with this identity. Okay. Rota-Baxter algebras have been studied pretty extensively, going back to Baxter, and Rota looked at them as well in the context of combinatorics and other areas. But we can think of these as generalizations of the standard integral operator. I know Li Guo, my collaborator, has done a lot of stuff working with Rota-Baxter algebras. In the literature, though, you don't really see kernels that are just functions of t. Usually they're functions of x as well as t. So another type of kernel we could look at is a separable kernel. This is when the kernel is, we can write it as a product, a function of x times a function of t. The benefit here is that the function of x doesn't depend on t, so we can pull it outside of the integral. And that's going to make computations a little bit simpler than just an arbitrary kernel, although even just with something like this, the Rota-Baxter identity from the previous slide no longer holds. So just a very simple example, if k of xt, the kernel is just x, and f and g are both 1, then we see the left-hand side of the Rota-Baxter identity ends up becoming x squared. The right-hand side is x to the 4th, I should say. The right-hand side is 2x to the 4th over 3. And so these are not equal. Right? And so just introducing a function of x in our kernel, it's going to complicate the computations a lot. In the separable case, though, we actually get something that's not quite different. It's a slight twist on the standard Rota-Baxter identity. And in fact, we call it a twisted Rota-Baxter identity. So this is the setup, right? So we have an open interval with a fixed lower limit. We have a family of separable kernels. So omega is some indexing set defining our family. And so for each little omega, we have a separable kernel. And let's assume that the functions of x are non-zero everywhere in my interval. So this is a restriction we have to place because what we're going to be doing is we're going to be dividing by the function of x. So we need to assume it's non-zero. And we're going to define these tau omegas. We're going to call these the twists. And tau omega is just k omega of x over k omega of a. A is the fixed lower limit of integration. And we can then define this family of separable Volterra integral operators like this. And it turns out that for any alpha and beta in my indexing set omega, the following identity 3 here holds. And this identity is very similar to the Rota-Baxter identity that I had a couple of slides ago, but there's this twist that you have to put in. So you notice inside the outer operator, we have this tau alpha inverse, and over here tau beta inverse, and then we're multiplying on the outside by tau alpha and tau beta. And so if the taus weren't functions of x, then we could pull them outside of the P and just cancel them out, and we would just get the standard Rota-Baxter identity. But because they're functions of x, we have to keep them in here. And basically what's going on is, because we have an iterated integral right here, right? P beta of P alpha, we're integrating an integral. So we can pull out the K alpha from this inner integral, but we cannot pull it out of the outer integral because it's a function of the outer limit of integration, the outer variable of integration. So we need to introduce this twist in order to make everything work out. That was a little vague. I don't have details, but I can show, if maybe later on during the second session, I can go over the details of that. Anyway, we call any algebra with a family of linear operators and invertible elements satisfying this identity 3. We call this a matching twisted Rota-Baxter algebra. I'll use just MTRBA, right? Matching twisted Rota-Baxter algebra. It turns out that we're not getting too much more having this matching, having this twisted Rota-Baxter algebra. We can actually always produce a standard matching Rota-Baxter algebra from that. Basically, what we do is we just define this new operator P check, which is defined as such down here. And if the algebra A, together with the operators P omega and the invertible elements tau omega, if that's a matching twisted Rota-Baxter algebra, then A with the P check operators is a matching Rota-Baxter algebra. And we're going to use this result later on, which will allow us to produce a matching twisted Rota-Baxter algebra. All right, so we've seen that what's going on, we have our algebra of continuous functions on some interval I, and we have some collection of kernels. And we've seen when we have a phantom kernels, certain identities are satisfied. When we have separable kernels, other identities are satisfied. These are the only two that we looked at in detail, but there are other types of kernels. For example, a lot of kernels you see are functions of x minus t, like 1 over x minus t or cosine of x minus t, things of that nature. And those aren't either of these. And we don't really have a good handle on what algebraic properties those integral operators with those kernels satisfy. And so what we want to do is we want to be able to develop a theory for these arbitrary integral equations that doesn't depend, that's independent of the specific kernel and the specific algebraic properties of that kernel. So let's just try to summarize what we want to do. We want to construct an integral polynomial algebra. And this algebra should consist of a collection of variable functions. So we have some set of indeterminates y. These are the unknown functions that we want to solve for in a given integral equation. We should also have a collection of integral operators. And these operators should depend on the limits of integration and the kernel. So basically, each kernel, we're going to have a separate integral operator. And if you change the limits of integration, that's also going to be a separate integral operator. All right, so for each, basically, you can think of it as a triple, right? The lower limit, upper limit, and the kernel. So for each triple, we're going to get a new operator. We also should have a collection of coefficient functions so that, so we could take the integral, and we could take e to the xt times the integral of something. And so that's that e to the xt, those are the coefficients. And then we want to put these together using the standard algebraic operations as well as the action of performing the integral. So let's see what we can do. Well, we are allowing for basically any integral operator with any kernel, and we don't know, depending on what the kernel is, the algebraic properties of that operator could be very different. And really the only thing connecting all of these integral operators is the fact that they're operators, sending an element from this algebra to another element of the algebra, and they're all linear, because all these integrals, every integral operator has to be linear. And so that's basically the only thing that we can work with. So if we fix some indexing set omega, we define an omega operated algebra. It's an algebra A together with a collection of linear maps from A to A. And that's basically it. And we can then define an operated algebra homomorphism to just be a homomorphism from one operated algebra to another that respects all of these linear maps. So this is the general setting, but the specific case that you should be thinking of for all of this is the algebra A is the algebra of continuous functions, and omega is an encoding of all of the integral limits and kernels, and the p omegas are the integral operators. So when we write p omega of f, that's the omega integral of f of t dt. And omega is encoding the limits of integration and the kernel. So just to give you an example here, let's say we had the operator sending f to the integral from 0 to x squared of x minus t times f of t dt. Well, we think of that as the omega integral, where omega is encoding the two limits of integration, 0 and x squared, and the kernel x minus t. Okay, so for each kernel and each pair of limits, we get a new operator. Right, so that's sort of what we want to be thinking of going forward. So this algebra, this operated algebra, this is going to be the coefficient algebra when we define our integral polynomial algebra. And the polynomial algebra itself is going to be what we call a relative operated algebra. So we're calling this a C of I p omega algebra. So here, this is our fixed operated algebra. And so we're defining a relative algebra with respect to this. So this is just another operated algebra together with the structure map, basically sending the elements of our base algebra into our new operated algebra R. And what we really care about is the free relative algebra over R of Y. And this is basically the free object in the category of all of these relative operated algebras. So basically, anytime you have a function from R of Y into another relative operated algebra, then we get this commutative diagram. This universal property is satisfied. And the integral polynomial algebra that we want to construct is going to be this free algebra that we've defined here. I'm going to give you a very basic, generalized construction of what this algebra is. I'm leaving out a lot of details, and we can talk, if you want to see more details, we can talk about that after the breakout session. So we have this fixed indexing set omega. If you have a module V, we can define what we call the omega bracket V. This is basically just a copy of V that's linearly independent. And then we can define V bracket omega to just be the direct sum of all of these V bracket little omegas. And elements here, we call them bracketed words. And so the idea is that omega bracket V, that's going to correspond to the omega integral of V when we actually work out the construction of the integral polynomials. And so to construct the free relative algebra, we do the following. We're going to define a directed system, IN, and each IN is augmented in the sense that we can write it as a direct sum of C of I with this IN plus for some IN plus. We want to think of the IN pluses as the elements of IN that contain our variable functions, and then the C of I, these are just the coefficients. And the way that IN is defined, I'm not giving you the definition here, the formal definition, but you can think of it as a symmetric algebra on the omega bracket of IN minus 1. Right? So there's a lot of detail I'm leaving out when I write that. But basically, we get this directed system, and then we're going to define I to be the direct limit of these INs. And you notice, because each IN is augmented in this manner, then I is also augmented, right? So we can write IN as C of I direct sum IN plus. Okay, like this, right? I is C of I direct sum I plus. And with this I, again, it's very general, the definition here. But we have some directed system. And now for each little omega, we can define a linear map pi omega from I to I. And so here is why we need to know the fact that I is augmented. It's C of I direct sum I plus, because any element U in I, well, the element, if U is in C of I, then we just define pi omega of U to be P omega of U, or where P omega is that omega integral that we defined earlier. And if it's an I plus, then we define it to be bracket omega of U. And so here we see that the bracket is our way of generalizing, of extending the integral operators, right? So the omega bracket of something is basically take the omega integral of that variable function that we have. That's what U is. And it's possible to show that this I, together with the pi omegas, that this is a relative operated algebra. And it turns out, after a lot of work, that this is the free relative operated algebra over R of Y. And so what that means is that when we have integral equations, we can polynomial integral equations, we can think of them as elements of this direct limit I. So that's very high level. Let me show you how we can really visualize this set. And that's using what are called vertex edge decorated rooted trees. So a tree is a graph with no cycles. A rooted tree is a tree that has a fixed element called the root, and all of the branches of the tree extend from that root element. And we're calling these vertex edge decorated rooted trees, meaning all the vertices and all of the edges have labels. And so when you look at this here are just a bunch of examples of some of these trees. So the edges are decorated by elements of omega, so the alphas, betas, and gammas, and so on. And the vertices are decorated by elements of this set Ci of Y. Right? And so we're assuming that the root vertex is any element of C of I of Y. So these are basically polynomials in our set Y with coefficients in C of I. And the leaf vertices, so basically the topmost vertex on every branch, is decorated by a polynomial, a non-constant polynomial. That's what the plus means. And so basically we're defining the set E to be the collection of all of these trees. And we can think of E as the set of just singletons that are decorated by elements of C of I, union E plus, where E plus, we're assuming that this singleton set is in C of I plus, and the trees are all decorated as such. Right? And then we have a collection of trees now, and we can formally define the module generated by these trees with coefficient over the algebra of continuous functions, the ring of continuous functions. So we're going to define two operations on these trees. The first we call the grafting product. This is where if we have two trees, we graft them together. And so what's going on here is you'll notice that we combine the roots. So you'll see we combine the root A and the root B to just be a single root. And since A and B are in an algebra, we can look at the element AB, and that's the new decoration for our new root. And then in terms of the branches, we just have the branches from the first tree and the branches from the second tree both sticking out of our root. So here's an example, right? We have these two trees and we stick them together. We graft them together as such. We're going to think of this as multiplying integrals, right? And we'll see the connection between trees and integrals in a second. We also can define an extension operator. So this is for each element omega, we can define lambda omega. And what this does is it creates a new tree which has a new root labeled by 1. And we have a branch from that new root to the old root. and that branch is labeled by omega. So we can see a couple of examples here. And we're going to think of the extension operator as an analog of the omega integral operator. And so on our set E, we can define what we call gamma omega. So this is basically taking its lambda omega in certain extents and in most instances. And if our tree is just the singleton, the single vertex, the single root labeled by an element of C of I, then gamma omega just continues to have that single root, but now it's labeled by P omega of that element A. And with this construction, we can prove that this collection of trees, together with the gamma omega operator, is isomorphic to the set of bracketed words I with the pi omega that was defined previously. And so that shows that this algebra of decorated rooted trees is also the free relative operated algebra over R of Y. And so when we want to look at integral equations, we'll see we can think of them as these trees. Let me just show you sort of the connection between the various algebras we looked at. So we're going to call an element of this set I, or equivalently this set E, we call this an integral polynomial algebra. And the integral operators are omegas. We have coefficient function space, algebra of continuous functions, and variables Y. And an equation phi equals 0, where phi is an element of either of these, we call that an integral equation. So here are just some examples. So the bottom row you can see are some integrals, and you want to think of these as integral equations by just setting them all equal to 0. So here we have some examples. We see like the elements A, B, C, D, and so on. These are polynomials in Y, in our variable Y, with coefficients in the algebra of continuous functions. That's what the Roman letters are, A, B, C, and D. And then the Greek letters, alpha, beta, gamma, and so on. These are elements of our set omega, and they're defining our integral operators. So remember, they're encoding like the limits of integration and the kernels. And so you see, we can like multiply integrals together. We can have iterated integrals. So here we're taking the alpha integral of this product of integrals. Right here we're multiplying this integral here by this iterated integral. So you can all different types of equations. And we can now think of this as an element, as a set of bracketed words, which is what this middle row is, or we can think of them as rooted trees. So you see the A times the alpha integral of B. Well, A is the outermost coefficient, and then the alpha integral, that's an edge up to B, and B we're labeling that next vertex. If we're multiplying two integrals together, well, that corresponds to a tree where we're branching. We're branching from the vertex A. If we have an iterated integral like this, right, we have the alpha integral of this product, the beta integral times the gamma integral. And so you see, we can translate any integral equation into a tree of this form. What this does, this gives us a formal way of considering equivalence of integral equations. So what we're going to do is, given any algebra homomorphism F from the algebra of continuous functions into C of I, well, we can define this uniquely depending given any map from the variable functions Y into C of I. And so basically we're going to think of these FYs as like defining what our solution set should be. So we have some collection Y1 up to YN, and we want to specify, okay, Y1 is this function, Y2 is this other function, and so on. And that defines a homomorphism from this polynomial algebra R of Y into the algebra of continuous functions. And because I is the free object in our category, we get an operated algebra homomorphism, F bar, from I into C of I. And so saying, given any element of I, any phi, which remember, we're thinking of the elements of I as our integral polynomials. So given any element, saying phi is 0, saying this equation has a solution means that f bar of phi is equal to 0. And we'll see an example of what that looks like. And now what we can say is if we let J sub Fy be the kernel of F bar, then if we take the intersection of all of these kernels, then the elements in J are precisely the algebraic operator identities that are satisfied by any element of C of I. So these are the distinct identities that will be true no matter what functions Y we input. And now we can say that two elements are equivalent if they have the same solution set, but having the same solution set means that their difference is in this set J. Okay, so we formally define what it means for two integral equations to be equivalent. Just to show you an example, we looked at this example of an integral equation earlier. So we saw that it had solution, y of x is just sine x. And so to see what this looks like in our more abstract construction, we can define the integral operator p omega defined as such. And so here omega is just encoding the variables of the limits of integration and the kernel. And so now we're fixing our single set y, and we can define f sub y, sending y, or just a single variable, into c of y by just sending it to be sine x. And that defines a unique map little f, which in turn defines a map f bar from the free object into the algebra of continuous functions. And so what we're saying now is because sine x is a solution to this equation, then if we define phi to be this element of I, you notice that this is the equivalent of this equation. We're just moving y to the other side. Then sine x has to be in the kernel of this f bar. Okay, so are we out of time? Sorry,
you have 3 more minutes if you.
Okay. Okay. So, all right. I don't know if I'll be able to finish this in 3 minutes, but we'll see what I can do. So what we've done is we've constructed an algebra of integral polynomials, and it really does work for any integral equation that you can think of. But as you saw, it's very general. And what we want to be able to do is we want to look more specifically at, we want to be able to look at more specific types of equations and see what else we can get, knowing that if we have like this, we're only working with these kernels or these limits of integration. And so what we were able to do was we focused on the case of separable kernels. So this is just all the information I had previously about separable kernels. Remember I said we saw that the separable kernels satisfied that matching twisted Rota-Baxter algebra identity. And we said that if that was the case, then you can define a new operator that was a matching Rota-Baxter operator. And so in this case, when this is our operator, our twisted Rota-Baxter operator, then P check ends up being this phi omega defined like this. And we can define relative matching twisted Rota-Baxter algebras and free relative matching twisted Rota-Baxter algebra in a very similar manner to what was done just in the arbitrary operated algebra case. And so let me try to give you a construction of how this works. And we're going to define the free relative matching twisted Rota-Baxter algebra. And it's this algebra here. And so we see it's a direct sum. We're taking this tensor product of this algebra here together with this tensor power. And so pure tensors in this algebra are of the following form. Okay, so the U's are elements in C of I of Y. So these are polynomials in Y with coefficients in C of I. And the omegas are in our big set omega. And any element, any pure tensor, we can think of as an iterated integral like this. Okay, so U naught, and then we have omega 1 integral of U1 times omega 2 integral of U2. And so these are all, we have these iterated integrals. And so the point here is we only want to be able to consider iterated integrals. And it's possible to define operators on this set. So we can define a product on this set, and we can define what we call rho f omega on this set. And the product is, and they're defined recursively, and I don't have the general formula written down because it's annoying and complicated. But just to give you some examples, right? So what we're trying to do here is we're trying to see what happens when we integrate something and when we multiply two integrals together. And so here are just some examples. If we have U is this pure tensor, and we perform this rho f omega of U, we end up getting this. And I'm not telling you where that comes from. It's as a result of the formal definition, but that corresponds to this this operation on integrals, which you can check will work if you have U naught times the omega 1 integral of U1, and you perform the omega integral of that element, you get the following form. And you notice we have a product of integrals here, and we don't want to have products of integrals, so we can define a star operator which takes products of tensors and translates it into more pure tensors. And so we see if we have these two integrals, we multiply them together, this is the result that we get. And this we can translate that into the general form. So it turns out we can prove, long story short, that this algebra together with this star product that I haven't defined, and with a collection of linear operators pf omega, and we have twists because we have twists from the original base algebra C of I with our original operators, that this is a free relative matching twisted Rota-Baxter algebra. And the whole point of this is that we're able to show that any polynomial integral equation can be thought of as equivalent to one that is operator linear. Here, operator linear means that any monomial is an iterated integral, doesn't contain any products of integrals. And the way that we do that is we basically define an isomorphism from the free operated algebra in mod this ideal here, where this is the twisted Rota-Baxter identity, and we can show that that's isomorphic to this free matching twisted Rota-Baxter algebra we just defined. And here's an example of how it works. If we have this specific kernel to be e to the t minus x, which is a separable kernel, is e to the minus x times e to the t. Our twist is just e to the minus x. And then if we take an equation like this, if we write it in an operator form, we get this equation here. You'll notice it involves products of integrals here, right? And we perform our twisted Rota-Baxter identity enough times, and we end up with the following equation here, which is no longer contains any products of integrals. It just has iterated integrals. You're iterating more integrals, right? Here we have one iterate. Here we have two iterates. Okay, so while we lose the product, we gain iterates in our integrals. Okay, so that's it. Thank you very much.
Let us thank Richard for his talk. Do we have any questions for Richard?
Yeah, I'd like to ask a question about the last part when you bring things to the integrate linear form. So just to clarify, so let's say I have a product of two integrals, right? So integral of A times integral of B. Mm-hmm. Isn't it true that I can always just move one integral inside another? So just write that it's integral of B times A. So like, this is not what you do. Or this is what you do.
So you have the integral of A times the integral of B, or is it the integral of the product A times?
No. Two integrals. Product of two integrals, and I just consider one of them as a constant and pull inside the other, just because I can pull the constant under the integral sign, right? So it's not what you're doing, or
no, that's not what we're doing, because so
now, like, what's exactly the specification of operator linearity, right? Because this way I can
right. So in the case that you're talking about, when you pull, yeah, so the integral of A is a constant with respect to the limit of integration in the B integral, right? And the variable of integration. But when you pull it inside, now it's still a constant, right? And so the iterated integrals we're considering is the inner integral, right, has upper limit, let's say T, and T is the variable of integration of the outer integral. So it truly is an iterated integral in that sense. When you have a product of things and you move one inside, you're not really doing anything, right? Because you still have to perform that inner integral and then perform the outer integral and multiply them together. So it is a little bit more nuanced in the case that we're doing.
Okay, yeah, thanks for clarifying. Now I understand the difference. Yeah, thank you.
Oh, Richard.
Yes.
This is William.
Hi.
Is the star operation multiplication associative?
Yes. Yes. It's a product. It's a product on this It's the product on this algebra. So it satisfies all the properties of a product on a ring.
Is that easy to see?
Is it easy to see? You have to. It's a little complicated because the star operator is defined recursively, depending on like the length of the tensors. So you have to basically prove it by induction that it works.
Thank you.
Do we have any other question for Richard? Okay, so if not, we'll move to the breakout room, and then we'll reconvene after some time and can ask more questions to Richard. Let's thank him again for his talk.